So in this video, we're going to look into something called PCA. Why do we use it? Where do we use it? How do we use it? And all the other factors. So PCA stands for Principal Component Analysis. So it's not a machine learning technique. Let's get that out of the section altogether. So that's we definitely will not consider this to be a machine learning technique because obviously it is not. So what is it and why do we use it? So it is basically used for something called dimensionality reduction. Now we understood that each and every feature brings in a new dimension if we go on to plot it. So if we have two x variables and one y variable, basically the entire number of dimensions is 3, correct? So you have 2x and one y. So there are 3 dimensions, 3 factors to the particular data set. If you have 1x and one y, so basically there are 2 dimensions, then you can plot it in a 2D graph like an x and an y axis. But when you have say 2x and one y, you will need a third axis z, which will increase the number of dimensions as well as in the graph. So you will have another axis z or z. So that's how the number of dimensions increase. Now, in general cases, we do not have, say, 13 or 14 dimensions. You have, say, 30, 40, 50 dimensions. And it is quite difficult for you to go ahead and select each and every one. Even if you do mutual information gain, sometimes the mutual information gain correlation is just abrupt. So so you need to understand that correlation is not causation again. So you cannot rely on it completely. Mutual information is also something similar that it does give you some information about the Y thing, but uh, just because of that, we cannot keep it. Even though we go on to filter using these methods, we still have a lot to filter out and use. So, say if we have 30 features and then we go on to filter it down to say 25 or 20 features is still a lot to compute. And these are just the number of columns that I'm talking about. There will be number of rows as well. Now the rows are not limited to 100, 200, 300. They go like way beyond 10,000, 20,000. So, and we cannot lose the rows on the information, and we cannot lose, we would like to keep as much of information that we have in the column sections as well. So what is the solution? How do we go about it? So we obviously understood what dimensionality is or what are dimensions. So dimensionality reduction is nothing but reducing the number of dimensions of the data set while keeping as much of information as possible. So let's take an example to understand this. So say if you have a picture of say 24 pixels by 24 pixels. Now that's going to be a really uh, pixelated image. Now the very term pixelated does inform you that you can see the pixels because they are that big, correct? Now going on to a picture of, or you can say that going on to see a the same picture in its original size, say 240 cross 240, will be really clear, correct? Because it has more information in it. Now, if I go on to compress it to 24 cross 24, it's still going to look the same, but will lose a lot of information and will look pixelated, correct? So that's how dimensionality reduction works. You try to keep as much information as possible, but whenever there is dimensionality reduction, there is always going to be data loss. There is, if a particular person or a particular blog or a particular video is saying that you can use dimensionality reduction and keep all the information that is possible, and you can uh, do this particular, image compression or video compression, and it's going to compress 100% and there is going to be no reduction in the quality, they're basically lying. There might be a low amount of it where you can use various optimization techniques to reduce the number of data loss or the amount of data loss, but there is no such technique up till now that uh, helps you reduce the dimension or the data or compress the data in such a way that there is no data loss. Okay, so what does PCA do for us? So PCA is just one of the several techniques that is used for dimensionality reduction. We only look into PCA in this particular case as in it is generally applied to all kinds of data. Okay, so we want to use a generic model. In our cases, you can always go ahead and search up more and look up more dimensionality reduction purposes, sorry, dimensionality reduction methods, and see what are the purposes or where are they used in particular. But you will see that PCA is kind of the first or second or in the top 5 list for this particular data set or for this particular problem, PCA is always going to be there because it's one of the most highly used data reduction or dimensionality reduction methods. So we are going to look into that. Now, what is PCA that we're talking about so much? So how is PCA calculated? So over here we have a data set. Now this is the second step actually. So just consider the X and the Y, and you have the data scattered over there. Now we need to pull the data to the middle of the origin. So you find out what is the middle of the entire data, and you find that this point exactly that is on the origin is the middle. So you pull the data down so that the middle point is on the origin. Okay, now this is important for principal component analysis because the principal components always, the principal component lines always pass through the origin. So keeping that in mind, we just pull the data down. Now, the first question that should have arisen in your head is, if I pull the data down, wouldn't that create a problem? Well, it will not, because if you do not change the data values or the data points, but you change the entire unit space of it. So this might sound a bit confusing, but just understand that you have just picked up the grid and placed it in a different area. Now that doesn't change the points because it is still related to each. So if I just consider that this is the most extremist point on the left side, or the most the point with the lowest values, it is still the point with the lowest values, correct? All the other points do have a higher value of them, and this is still the highest, correct? So relatively, it is still the same, just that I've pulled it in a different manner so that I can use PCA on it. Now, uh, there is an orthogonal transformation that happens while using PCA, but I'll try to explain it as simply as possible. So we have done regressions, right? So just consider that this is a scatter plot and we want to fit a regression line. Now the regression line has, now this particular regression line has a criteria that we obviously need to reduce the residuals, but it also needs to pass through the origin. So each and every line that I make should pass through the origin, and I'm only going to consider the one that has the uh, least amount of residuals, obviously, and passes through the origin. Now in this particular case, the green line over here, PCA1 or principal component 1, gives us that. Okay. Now that is one aspect of it. Now I could explain the direction of it, or I can go on to predict most of it, but what about the dispersion? So I will need a second principal for that, principal component for that. So I go on to create a similar thing using the other principal. Now they have to be 90 degrees to each other. Okay, now that is one of the aspects of principal components, that they are at 90 degree to each other. Now this is what is explained. So there are two column vectors, and when you convert them to PCA, they become in 90 degrees. So this is what happens in a two-dimensional space. In higher dimensions, it goes on to become a bit different. Now, generally, if you go on to visualize a principal component, it would look something like this. But coming back here, you can see that, so that was about principal components and how you create it, but I'm going to help you observe a few facts that are quite important. Now, I'm making a statement that principal component 1 has a higher order, or I should say, is more contributes more to the prediction, because, or it contributes more than principal component 2, and I'm going to try to explain you how does it do that. So consider this point x1, and you see that for every we'll just take approximations here. So for every 4 units of x of feature 1, there is a 1 unit change in feature 2, correct? So if I go on to fit a line in such a way that it goes on to explain me the spread on the horizontal axis, it's going to be of a higher order because it explains more amount of spread of the data, correct? So it's consider if this would have been a circle, and if I would have had the same principal axes, they would have been of the same order, right? Or there wouldn't have been a principal component 1 or 2. They would have explained the same thing because the data is perfectly circular. Now, coming back to this particular example, I see that the data is spread less along this axis than on this axis. Okay, let's just take principal component lines to be a better estimator. So this line explains more the variation than this line. Okay, so that's why principal component 1 is more important than principal component. Now, this is a fact that usually people go on to forget. But again, this was an example of 2 dimensions. You can always have it in higher dimensions, but going beyond third dimension is impossible to go ahead and draw in the first place because humans cannot visualize data more than 3 dimensions. So in 3 dimensions, it would go on to compress it in such a way that you can have a plot, you can have the graph plotted in 2 dimensions. So you can, how do you go on to see that your PCA has done a good job? Let's see how do you do that. So here we look into the practical aspect of PCA, and I'm using the data set of class from UCIML. That is a pretty good website. You should go out and look that up. But here it's on Kaggle, and I'm creating the notebook in Kaggle as well. So this is the link to the data set. Go ahead and have a look. I'm using all the I'm using, I think all of them are pretty familiar to you apart from min-max scaling, PCA, and pipelining. We're going to understand that one by one. So importing the data is I'll just run all the sections. Take a single minute. Yeah. So this is what the data looks like. You can always go ahead and look at the data description and try to understand what is what and so on and so forth. But let's just understand the data as it is. So I have these columns. They are all float values and the type is just an integer. So that's good for us. We no need of label encoding. I want to describe and I do not see a high amount of outliers as well. They are more or less fine. Yeah, they're more or less fine. Okay, I can see that there are 7 types of classes. Okay. Yeah, there are 7 types of classes here. And I'm just using a scatter plot and against Ri and Na, and then trying to plot I'm just trying to plot the graph in such a way that I can visualize which graph is what. But it's not that greatly understood. Like I cannot just say, okay, this is one cluster, this is another cluster. There are some points that I can still figure out, like, okay, this is a single cluster here, there is one cluster here. There are a few points here and there. How do I go on and handle them? So let's do a bit of data transformation. First, I'm going to use min-max scaling. Now, min-max scaling is basically going to scale the data in such a way that my data will lie within 0 and 1. So it basically compresses the data in terms of percentages if I have to put it in a way. So say the lowest value that I have is 0 and the highest value that I have is 10. After using min-max scaling, my highest value will be 1 and my lowest value will be 0. Now you might say, okay, now you change the values exactly, but I did not change the values. I have scaled it in such a way that it represents the same thing, but uses less number of units. Okay, and what do I mean by that? So say if I have a data 1 there and so I have 0, 1, so I've got 10 points. Let's just consider that I have 10 points, 0 to 10. So my minimum value is 0 and my maximum value is 10. Now, after doing min-max scaling, my values that I will get is 0, 0 0.1, 0 0.2, so on till 1. The values basically range from 0 to 1, and that's how you go about it. So this is one kind of scaling. You can also use standard scalar where the entire distribution is taken into consideration and the mean is set to 0 and the standard deviation is 1 and the entire data is distributed in the terms of standard deviation. So that's so the values are basically standard deviations and not the original values. But again, they are also basically the scaled version of the same. So you can interpret them in a similar way like we just did for min-max scalar. Now, going ahead, I just wanted to view the scaled DF. So it looks something like this. Now for using min-max scalar, you just go on to import sklearn.preprocessing, import min-max scalar from there, make a object of it. and then use minmax.fit and send in the data frame that you want to uh, go on to, pre-process, if I have to put it in a way. Yeah. So now you have the scaled DF after transforming it. So after fitting the data, you also need to transform it. Or you can just use fit transform. That does the job as well. Okay. So okay, let's just try that out. I go on to say fit underscore transform, and then I run both the things and I get the same thing, correct? So that also does the job. Just in case if you want to have two different steps for other reasons, you can have that as well. Now, let's look at how do you go on to do PCA. So it comes from the decomposition module. I go on to import from sklearn.decompose import PCA, and I go on to mention the number of components that I want after the decomposition. So I want it to compress my entire data into two columns. Okay. So my entire data gets compressed to two columns here. And I want to print the 5 first records. So that's the only reason I'm doing it. Again, over here, when you do PCA.fit, it basically fits the entire, it takes into consideration the entire NumPy array that you have passed in here, that is scaled and then uses PCA methods to go on to transform it accordingly. And then I'm just storing it to PCA. So that's how PCA works, and this is just for printing the first 5 records. If you want to just print the first 10 records, you just do this, and that gives you the first 10 records. But I want to keep it to 5, so that gives me an intuition, so I do not need to look at more data. But that's what it is, more or less. Now, after understanding this, I would want to see the shape of the data as well. So I saw that after the scale DF initially had 214 records and 10 columns. Now it has 214 records, so the records did not change, but the number of columns is 2. Okay. Now let's look at the scatter plot. And I'm using the very same scatter plot here. And no, so it's not exactly the same. So this doesn't mean the first column and the second column. We saw that there are two principal components that are very, very different from the features. Now they do not represent the feature in any way. It is a compressed form of it. So I'm just printing the first values as X and the second value that are there in the NumPy array as Y. And then I'm using main df.type as my hue so that I can have the labels. So you see that it's better than the initial graph that we saw. I can see that there are a few clusters here. I can see a cluster here, a cluster here, and a cluster here. Well, it is not linearly separable, obviously, but it did capture or did keep intact a lot of data, correct? So that was one thing. Now let's look at, let's implement the model and try to understand how better or how good it is. So in this particular example, we are not trying to make a model that is, works great and so on. I'm just trying to explain that even after doing PCA, okay, the data is such that the accuracy either increases or remains the same. Okay, so let's just try that out. So I'm shifting it to X and Y, and it's the same thing, and then splitting the data over here using the random state as 121. Doesn't make a difference, you can have any value. And I'm setting the test size as 0.2. That means I'm just using 20% of the data for my testing purpose. And the shapes are such that I mentioned here. Now you see that the data isn't scaled, the data isn't transformed. I'm using the actual main DF. I'm not using scaled DF or XPCA and so on. That was just for explanation purposes. Now I'm using the main DF for train and test. So my data isn't scaled, nor does it have the PCA values. Okay. So now going down, I go on to import the K nearest classifier, and given just basic values, I'm considering 5 neighbors as an example, and the algorithm should be brute. Okay, so brute force basically. Now I go on to fit my KNN model. Sorry, I want to fit my KNN model, and I fit the data X train and Y train to it. Now I print out the score that it gives for KNN. Now, because of the higher number of classes and lower number of records, there have there has to be a few confusions, as we saw even in the data that there were overlaps. So there are going to be misclassifications, and 0.558 is, according to me, is quite a good score considering that there are 7 classes and really low number of records that I'm using for testing. Okay, so that's fine. We are not looking into the accuracy part of it for this example. We're just trying to understand and implement PCA and a few other concepts here and there. So I'm going to use something called the pipeline. Now, a pipeline is basically, as it sounds, it's basically a pipeline. Now, if you're going to take a real life example of a pipeline, it is basically used to transport something from one end to the other end. Consider your uh, water pipeline. So basically, the filtration is done through the pipelines, and the water is sent. Filtration is done. It is sent to your houses and used for the other purposes. So that's what it happens here. Okay, so the filtration aspect is done over here and then sent into the K nearest neighbor. So you pipeline initially is fitted with the values. So I'll just explain it in brief. It's pretty counterintuitive because I've labeled it in the right manner to understand what part of it explains what. So my data comes in. Now I have to process it just like I have to process the water in the water filtration plants. So I need to use min-max scaling for that because I've used that for this particular example. You can also use standard scaler, not an issue. And you do min-max scaling and just label it here just in case. And then you have PCA. I'm doing the PCA for 6 components. So I'm reducing the number of components from 9 to 6. I'm reducing it by 3 dimensions. Okay. And now this is basically the final output, like using the water at your homes. I'm sending it to KNN, which will give me the final output. Okay. So this is the entire pipeline. I'm storing it to a variable called pipeline. Now pipeline.fit xtrain will basically send the entire values here and it will give me an outcome after I do pipeline.score. Pipeline.score will basically give me x test and y test. Giving it x test and y test values will give me the score after doing the pre-processing from min-max scaling, converting the entire data into 6 components, after doing PCA, after implementing PCA, and then trying to get the values. So it is both for training as well as for testing purpose. So the pipeline is implemented for both training and testing purpose. Okay. So if we did not use a pipeline, we had to use 3 to 4 steps for first scaling the training aspect of it and then scaling it for the testing purpose of it. But that would have solved the problem in the local scenario. Okay, so what do I mean by local scenario? Now, basically the data that you're using here is static. Okay, so you have the data set with you, you are basically splitting it into train and test and then using it. But in general cases, when you have a model which is performing good and the particular company or whoever you're building the model for or whatever reason you're building the model for, they basically need the model in such a way that they can just use the model and get the output. They're not going to sit and pre-process the data and then send it to the model. So in those places, pipeline helps a lot. So you just feed in the data that you have and go on to make the predictions accordingly. Okay, so that's a pretty good thing. Now, again, fitting the data, getting the accuracy. You see that I have got the exact amount of accuracies with just 6 uh, components. So now instead of having 9 columns, you can just consider that I used 6 columns and got the same values. And I did not need to, I did not even do uh, feature importance. I did not do correlations and understood them, made a separate column for them, and then implemented it. I just used PCA and that did the job for me. Okay, so that's one. Let's just reduce it, the number of components and see what happens. So you see that even with 2 components, my accuracy reduces by only 2.3 or 2.4%. Okay, which is an acceptable amount because I'm just using 2 components to go on to predict the values. So from 9, I'm reducing the number of components to 2, which is quite a reduction. and you can see that the data that is lost, obviously there is some amount of data lost, and that affects the accuracy of it, but it does give you a good accuracy even with two components. That's a good thing that you need to look into. Now, that was all about scaling, about PCA and minmax. Minmax scaling, PCA, and pipelining. I recommend you guys to create a different pipeline and use a different scaling method and try to see what happens. So that is your homework here. Basically go on to have uh, a different pipeline. So what do I mean by a different pipeline? You have a decision tree. For example, take in the model as decision tree, and then go on for standard scalar. Just use standard scaling for scaling purposes. Obviously, you're going to use PCA as well, and then try to either improve the accuracy or try to optimize it up to the same level. So I know that having six components gives you the exact amount of accuracy. Having seven, what does seven do? It reduces the accuracy. It's not good. Having eight also gives you the same amount of accuracy. What happens with nine? It gives you the same amount of accuracy. So I see that six gives you the best amount of accuracy. You can always use a for loop to check this out as well. So four also gives you the same amount of accuracy. So I'm going to keep it at four. Okay. So you can see that I have reduced it to four now. From nine, you have four components that are giving you the same accuracy. So that's how you go on to see that is the best for this particular thing. So I'll just reorder it so that you guys do not get confused with the flow of the data, and the model is basically decision tree. So now what you're going to do is you're going to create a pipeline for this and then go on to fit the model and see how does it work. Okay, so that was about all that you needed to know in machine learning and other aspects of it. Let's try to implement your learning in a more constructive way and try to work on a project.